March 1944, somewhere over occupied France. A formation of Luftwaffe Focke-Wulf 190s spots what looks like easy prey below them. American P-47 Thunderbolts, lumbering through the sky like flying bathtubs. The German pilots know these aircraft heavy, slow to climb, predictable, they dive. But something's different today. The P-47s don't run. They don't dive away using their weight advantage. Instead, they do something that should be impossible. They climb, hard, fast, aggressively. The Thunderbolts pull up at an angle that makes the German pilots' eyes widen in disbelief. These same American fighters that struggled to climb just months ago are now ascending like rockets, meeting the Fu-190s head-on before the German pilots can process what's happening. One Luftwaffe ace would later write in his report, "The American Thunderbolts climbed at rates we had never before observed. Our tactical advantage was completely negated. What the Germans didn't know was that these P-47s carried something new, something that looked almost comically simple. The propeller blades were wider, paddle-shaped. Engineers had called the idea crazy when they first saw it. But those wider blades were extracting every ounce of power from the massive Pratt and Whitney engines. The result? A climb rate increase of more than 600 feet per minute. Performance improvements that translated to speeds over 100 miles per hour, faster in certain conditions. The Germans weren't fighting the same airplane anymore. This is the story of how one engineer's obsession with propeller design changed the course of aerial warfare. A story that begins not in the skies over Europe, but in a dusty field in Ohio 25 years earlier. December 1917, McCook Field, Dayton, Ohio. Frank Walker. Caldwell steps off the train into a biting winter wind. He's 28 years old, mighty graduate, mechanical engineer. He's just been appointed chief engineer of the Propeller Research Department for the U.S. Army Air Service. The field around him is chaos. World War I is raging across the Atlantic. America needs fighter planes, bombers, observation aircraft, and they need them now. But there's a problem that's killing pilots before they ever see combat. Propellers are falling apart. Literally. Caldwell walks into a warehouse filled with wreckage, shattered wooden propeller blades. Some split lengthwise, others delaminated into useless strips of wood and glue. Aircraft are crashing on training flights because their propellers disintegrate mid-flight. The propeller, one report states, remains the least understood element of aircraft design. Caldwell picks up a broken blade. He knows this isn't just about better glue or stronger wood. The entire science of propeller design is fundamentally flawed. In 1917, propellers are essentially afterthoughts. Carved chunks of wood bolted to an engine shaft. Pilots get whatever blade pitch the manufacturer decided to provide. Fine pitch for takeoff and climb? You'll struggle at cruising altitude. Coarse pitch for high-speed cruise? Good luck getting off the ground. It's like driving a car stuck in one gear forever. Caldwell's colleague at McCook Field, Major Elmer Nadler, describes the situation bluntly. We're asking pilots to fly aircraft with propulsion systems that can only operate efficiently in one specific flight regime. It's not just inefficient. It's dangerous. The problem runs deeper than anyone realizes. As engines become more powerful, the mismatch between engine capability and propeller efficiency grows worse. The Army's new Liberty engines produce over 400 horsepower, but the fixed-pitch wooden propellers can't efficiently convert that power into thrust across different flight conditions. Think about it this way. A fixed-pitch propeller optimized for takeoff provides maximum grip on the air at low speeds like a car in first gear. Great for getting airborne. But once you're flying fast at altitude, those same blade angles are fighting through the air inefficiently, wasting fuel and limiting speed. Conversely, a propeller pitched for high-speed cruise slices through the air beautifully at altitude. But during takeoff and climb, it doesn't bite the air aggressively enough. Your takeoff roll becomes dangerously long. Your climb rate suffers. In combat, that means you're dead. Pilots are forced to choose. Do you want to get off the ground quickly? Or do you want to fly fast? You can't have both. Caldwell refuses to accept this limitation. He starts by doing what no one else has systematically done, actually testing propellers under controlled conditions. He designed something he calls the whirl test. Mount a propeller on a fixed stand. Spin it at various speeds. Measure thrust, efficiency, vibration, structural stress. The results shock everyone. The best propellers of 1918 are only about 65% efficient. That means 35% of the engine's power is being wasted, converted into heat and turbulence instead of forward thrust. Worse, Caldwell discovers that propeller efficiency drops dramatically as flight speed increases. The faster you fly, the less efficient your propeller becomes. The very thing designed to pull you through the air is increasingly working against you. But there's an idea forming in Caldwell's mind. What if the propeller blade angle could change? What if pilots could adjust the pitch for different flight conditions? Ground-adjustable propellers already exist in crude form. Mechanics can loosen bolts, rotate the blades, and lock them at a new angle before the next flight. But that's not a solution. That's a compromise. Caldwell envisions something revolutionary. A propeller that could change pitch during flight. Automatically, continuously, responding to changing speed and altitude without pilot input. His colleagues think he's chasing an impossible dream. The mechanical challenges are enormous. How do you create a mechanism that can change blade angle while spinning at 1,500 revolutions per minute? How do you make it strong enough to withstand the massive centrifugal forces trying to tear the blades off? How do you make it reliable enough that pilots will trust their lives to it? The skeptics have good reason to doubt. European engineers are pursuing similar ideas using complex mechanical systems, springs, counterweights, intricate linkages. The designs are heavy, unreliable, and prone to failure. Caldwell suspects they're approaching the problem wrong. Mechanical systems have too many parts, too many failure points. What he needs is something simpler, more elegant. By 1928, after a decade of research and testing at McCook Field and its successor, Wright Field, Caldwell has developed the theoretical framework. He understands the aerodynamics. He knows what the propeller needs to do. Now he just needs to build it. That same year, he receives an offer from the Hamilton Standard Propeller Corporation in Connecticut. They want him as their chief engineer. They're willing to give him resources, freedom to experiment, a chance to turn theory into reality. Caldwell accepts. He leaves government service and walks into a company workshop in East Hartford. On the wall, a sign reads, "The propeller is the gearbox of the sky." Caldwell smiles. He's about to prove that statement more true than anyone imagines. But first, he needs to solve a problem that has stumped the best engineers in America and Europe. He needs to figure out how to make metal blades change their angle in mid-flight, using a system so reliable that pilots will stake their lives on it thousands of times without a second thought. The solution, when it comes, will seem almost obvious in hindsight. Almost. Hamilton Standard Propeller Corporation, East Hartford, Connecticut. Frank Caldwell stands in front of a workbench covered with hydraulic components, cylinders, pistons, valves, oil lines. He's been staring at these parts for weeks. The breakthrough comes from an unexpected direction. Oil. Not as a lubricant. As a power source, aircraft engines are already filled with pressurized oil circulating through their systems. What if he could tap into that existing oil pressure to move the propeller blades? No complex mechanical linkages, no delicate springs, just hydraulic pressure pushing pistons that rotate the blades. It's elegant. It's simple. And simple systems are reliable, Caldwell sketches furiously. The basic design takes shape quickly. Each propeller blade sits in a hub. Inside the hub, a hydraulic cylinder connects to each blade root. Pump high-pressure oil into the cylinder and the blade rotates toward coarse pitch. Release the pressure, and centrifugal force and counterweights swing the blade back toward fine pitch. He builds the first prototype by hand May 25, 1929. He files patent number 193-612 for a propeller, though that bland title conceals what will become one of aviation's most important inventions. The early tests are promising. The propeller changes pitch. The hydraulic system works, but it's only two positions, fine for takeoff and climb, coarse for cruise. The pilot manually selects which position using a cockpit control. It's an improvement, but Caldwell knows it's not enough. He wants more. He wants the propeller to automatically maintain constant RPM, regardless of flight speed or power setting. He wants it to be truly automatic, the gear shift of the air that adjusts continuously without pilot intervention. This requires something more sophisticated. A governor, a mechanism that senses engine RPM and automatically adjusts blade pitch to maintain the desired rotational speed. Caldwell teams up with the Woodward Governor Company, They're experts in automatic speed control for industrial machinery. Together, they develop a centrifugal governor that responds to changes in propeller RPM by modulating oil pressure to the pitch change mechanism. The theory is sound. Making it work in practice takes 2 more years of testing. Boeing Field, Seattle, Washington. The Boeing Model 247 is the most advanced airliner in the world. All-metal construction. Retractable landing gear. 2 Pratt & Whitney Wasp engines producing 550 horsepower each. But it has a problem. The Rocky Mountains. The 247 struggles to climb above 6,000 feet with a full passenger load. For United Airlines trying to establish transcontinental service, this is unacceptable. The routes over the Rockies require flying above 10,000 feet, sometimes higher in bad weather. Hamilton Standard's chief test pilot, William Bill Cherry, has an idea. Fit Caldwell's new controllable pitch propeller to a Model 247. See what happens February 1933. 247 fitted with Caldwell's hydraulic controllable pitch propellers lifts off from Boeing Field. Cherry advances the throttles and pulls. Back on the yoke, the aircraft climbs like nothing he's experienced before. The climb rate increases by 22%. Takeoff distance shortens by 20%. Cruising speed improves by 5%. The 247 clears the Rockies easily with power to spare. Cherry lands. He finds Caldwell. 2 words. It works. United Airlines immediately orders Hamilton Standard controllable pitch propellers for their entire 247 fleet. Douglas Aircraft orders them for their new DC-2 airliner. Every major aircraft manufacturer wants them. Aviation will never be the same. The National Aeronautic Association notices. In December 1933, they award the Collier Trophy, American aviation's highest honor, to Hamilton Standard Propeller Corporation, with particular credit to Frank W. Caldwell, chief engineer, for development of the controllable pitch propeller. June 1934. The White House. Washington, D.C. President Franklin D. Roosevelt shakes Caldwell's hand in the Oval Office. Photographers capture the moment. The president congratulates him on revolutionizing aviation. But Caldwell's mind is already racing ahead. The 2-position hydraulic propeller is good. The constant speed version being developed is better. But he's envisioning something even more capable. He wants a fully automatic constant speed propeller with an additional critical feature: feathering. Feathering means rotating the blade to align with the airflow, essentially edge on to the wind. Why does this matter? Because when an engine fails on a multi-engine aircraft, a windmilling propeller creates massive drag. It's like flying with a barn door attached to your wing. Many twin-engine aircraft accidents happen because the drag from a dead engine overwhelms the thrust from the working engine. If you can feather the propeller, streamline it, you eliminate most of that drag. The aircraft can continue flying on one engine safely. This isn't a theoretical concern. Pilots are dying because they can't feather failed propellers. Caldwell and his team developed the hydromatic propeller. Full constant speed operation plus automatic feathering capability. Oil pressure moves the blades through their entire range of motion. A governor maintains constant RPM, and when an engine fails, the pilot can feather the propeller with a single switch. By 1935, the hydromatic propeller enters production. It's fitted to the Boeing B-17 Flying Fortress, the Douglas B-18, the Martin B-10, the Douglas DC-3, every major military and commercial aircraft being built. The Institute of Aeronautical Sciences awards Caldwell the Sylvanus Albert Reed Award in 1935 for investigations having a beneficial influence on the development of practical aeronautics. Then war comes. September 1939. Germany invades Poland. Europe explodes into conflict. The United States begins a massive military expansion. The Army Air Corps needs fighters, bombers, transport aircraft. Thousands of them, and every single one needs propellers. Hamilton Standard becomes the beating heart of American air power. Working 3 shifts, 24 hours a day, the factory produces hydromatic propellers by the thousands. Caldwell oversees the engineering teams ensuring quality, improving designs, solving problems. The P-38 Lightning gets them. The P-40 Warhawk gets them. The B-24 Liberator gets them. The B-29 Super Fortress gets them. The C-47 Transport gets them. The Navy's F-4U Corsair and F-6F Hellcat get them. By the end of World War II, Hamilton Standard will produce over 500,000 propellers. Virtually every American frontline aircraft flies with Caldwell's invention spinning on its nose. But there's one more revolution waiting. And it doesn't come from Caldwell's team. Early 1943, Republic Aviation, Farmingdale, New York. The P-47 Thunderbolt is a beast. 7 tons of aircraft wrapped around the most powerful engine in the world. The Pratt & Whitney R2800 Double Wasp. 18 cylinders. 2,000 horsepower. It can dive faster than anything else in the sky, but it can't climb worth a damn. Pilots complain constantly. The P-47 takes forever to reach combat altitude. German fighters can outclimb it easily at low to medium altitudes. That's not just inconvenient. It's lethal. The problem isn't the engine. The R2800 has power to spare. The problem is the propeller can't efficiently convert all that torque into thrust at lower altitudes. Engineers at Curtiss Propeller Division and Hamilton Standard start experimenting with a radical idea. What if they made the propeller blades wider, much wider? Instead of relatively narrow blades that look like thin spears, create blades with broader chord, more blade area to grab the air. The concept isn't new. Ships use wide propeller blades, but conventional wisdom says wide blades are less efficient for aircraft because they create more drag. The math suggests it won't work. They try it anyway. They call them paddle blades because that's exactly what they look like. Wider, broader, almost paddle-shaped compared to the narrow toothpick blades on earlier propellers. The Curtiss electric paddle blade propeller measures 13 feet 1 and 7 to 8 inches in diameter. The 4 blades are significantly wider than the previous 12-foot 2-inch narrow blade design. More blade area means more air being moved with each revolution. Hamilton Standard develops their version too. The paddle blade Hamilton Standard hydromatic propeller for the P-47 test pilot Bob Hoover later described his first flight in a P-47 with paddle blade props. I couldn't believe it. Same airplane, same engine, completely different performance. January 1944. The first P-47s, fitted with paddle blade propellers, arrive in Europe. The performance difference shocks everyone, including the Germans. Climb rate at lower altitudes increases by more than 600 feet per minute. At sea level, the P-47D with paddle blades climbs at over 3,000 feet per minute. The older narrow blade models struggled to manage 2,400 feet per minute. At 15,000 feet, the improvement is even more dramatic. Paddle blade P-47s maintain climb rates that narrow blade versions can't match. Suddenly, the flying milk jug becomes a climbing machine. German fighter pilots who'd grown accustomed to the Thunderbolt's predictable limitations find themselves facing a transformed adversary. Luftwaffe combat reports from spring 1944 repeatedly mention improved American fighter climbing performance. One German ace, Oberleutnant Heinz Knucke, writes in his diary, "The Thunderbolts climb now with astonishing rate. Our altitude advantage disappears before we can exploit it. This is most troubling. The P-38 Lightning receives paddle blade props too. Same story. Dramatic climb rate improvements, better acceleration, enhanced combat effectiveness. Even the Navy's F-4U Corsair gets paddle blades. The already formidable Whistling Death becomes even more lethal with improved climb performance. But here's what's remarkable. The speed increase that gives this story its title. At certain altitudes and power settings, paddle blade propellers allow P-47s to achieve speeds over 430 miles per hour, more than 100 mph faster than the same aircraft with older fixed-pitch propellers would achieve in similar conditions. The combination of Caldwell's constant speed hydromatic mechanism and the increased blade area creates unprecedented performance. The math works because paddle blades increase solidity, the ratio of blade area to total propeller disc area. More solidity means more efficient thrust generation at high power settings. The slightly increased drag is more than offset by dramatically improved thrust, especially at lower altitudes where American fighters do most of their combat fighting. Technical test reports document the improvements precisely. An ACA report number L135 titled, Climb and High-Speed Tests of a Curtiss 741C212, 4-blade propeller on the Republic P-47C. Airplane provides exact numbers. The data is irrefutable. Back in Connecticut, Caldwell watches these developments with satisfaction. The paddle blade breakthrough built upon his foundational constant-speed propeller invention. Without the hydromatic mechanism automatically adjusting pitch, Paddle blades would lose their efficiency advantages at different flight speeds. It's the complete system, automatic pitch, control plus optimized blade geometry that revolutionizes fighter performance. By mid-1944, the 8th Air Force flying from England and the 9th Air Force supporting the invasion of Europe operate thousands of fighters equipped with paddle blade constant speed propellers. The performance advantage over earlier models is so significant that older aircraft are retrofitted whenever possible. Pilots love them. Lieutenant Colonel Francis Gabreski, America's leading ace in Europe with 28 victories, flies a P-47 with paddle blade props. He describes the aircraft as the ultimate version of the Thunderbolt. It finally had the climb rate to match its speed and firepower. The technology spreads beyond fighters. B-17 and B-24 bombers use 4-blade Hamilton standard paddle blade propellers. The improved efficiency increases range and payload capacity. The C-47 transport uses them. Even the massive B-29 Superfortress that will eventually drop atomic bombs on Japan uses 4-blade Hamilton standard propellers based on Caldwell's designs. American air superiority over Europe and the Pacific rests partly on the spinning blades pulling those aircraft through hostile skies. Propellers that automatically adjust pitch thousands of times per flight. Propellers that feather when engines fail, bringing crews home alive. Propellers designed by a quiet engineer from Tennessee who just wanted to solve an interesting problem. May 8, 1945, VE Day. The war in Europe ends August 15, 1945, VJ Day. Japan surrenders, World War II is over. The statistics are staggering. America produced over 300,000 military aircraft during the war. Virtually everyone flew with Hamilton Standard or Curtiss propellers incorporating Caldwell's inventions. Those 500,000 propellers represented more than engineering achievement. They represented thousands of missions flown successfully, thousands of crews brought home safely when engines failed, but feathering propellers allowed controlled flight, thousands of combat victories enabled by superior climb, rates and speed. The American Society of Mechanical Engineers calculates that constant speed propellers improved overall aircraft efficiency by approximately 15% compared to the best fixed-pitch designs. That might not sound dramatic, but 15% better efficiency translates to 15% more range, or 15% faster speeds, or 15% better climb rates. In aerial combat, 15% advantage means the difference between victory and defeat, between living and dying. General Henry Hap Arnold, commanding general of the U.S. Army Air Forces, writes in his post-war report, "The development of the constant speed controllable pitch propeller ranks among the most significant technical achievements enabling American air superiority. This single technology provided measurable advantages across every category of aircraft performance." But Caldwell doesn't dwell on the war. His mind is already focused on the future. The Institute of Aeronautical Sciences awards Caldwell an honorary fellowship, recognizing his lifetime contributions to aviation. He's 57 years old. Many engineers would consider retirement. Caldwell returns to his office at the United Aircraft Corporation Research Division and keeps working. He becomes director of the Research Division, overseeing development of new technologies for the emerging jet age. While jets don't need propellers for propulsion, turboprop engines, jets driving propellers, represent another frontier. Caldwell's team works on propellers for the new turboprop era. He also focuses on helicopters. Helicopter rotors are essentially rotating wings, and the principles of variable pitch design apply. Hamilton Standard develops automatic blade pitch control systems for helicopters based on Caldwell's constant speed governor concepts. But perhaps his greatest satisfaction comes from seeing how completely his invention has been adopted. By the early 1950s, essentially every propeller-driven aircraft flying uses some form of constant speed, variable pitch propeller. What seemed radical in 1933 is now standard practice. The Wright brothers' 1903 Flyer used fixed-pitch wooden propellers that Orville and Wilbur carved themselves. Just 50 years later, aircraft fly with sophisticated hydraulic, constant-speed propellers that automatically optimize performance throughout flight. That transformation from hand-carved wood to automatic hydraulic systems defines the pace of aviation's golden age, and Frank Caldwell stood at the center of that revolution. After 25 years with Hamilton Standard and United Aircraft, Caldwell retires at age 65. He leaves behind an engineering legacy few can match. The patents he holds, the papers he published, the propellers bearing his designs that continue flying worldwide. But more than that, he leaves behind a philosophy, an approach to engineering problems. Start with fundamentals. Understand the physics completely. Don't accept conventional wisdom if testing suggests alternatives. Build systems as simple as possible. Test rigorously. Improve continuously. December 23, 1974. West Hartford, Connecticut. Frank Walker. Caldwell dies 3 days after his 85th birthday. The obituaries note his 1933 Collier Trophy, his patents, his contributions to aviation. But they can't fully capture what his work meant to the thousands of pilots who trusted their lives to his propellers. The bomber crews who made it home on 3 engines because feathering eliminated drag from the 4th. The fighter pilots who climbed faster, flew farther, fought better because their propellers efficiently converted engine power to thrust. The American Society of Mechanical Engineers designates the Hamilton Standard Hydromatic Propeller as an international, historic mechanical engineering landmark. A plaque at the New England Air Museum reads, "This propeller represented a major advance in propeller design and laid the groundwork for modern propeller aircraft." The irony isn't lost on aviation historians. Caldwell's most visible achievement, the paddle blade revolution of 1944, actually came from other engineers building on his foundation. Caldwell created the constant speed mechanism that made paddle blades practical. Without automatic pitch control, wider blades would be inefficient at different flight speeds. It's the perfect illustration of how engineering progress works. Foundational inventions enable subsequent innovations. Caldwell's hydromatic propeller created the platform that allowed paddle blade geometry to flourish. That's the real story. Not one brilliant innovation, but a systematic approach to solving problems that enabled decades of improvements. Caldwell didn't just invent a better propeller. He invented the system that allowed propellers to continuously improve. Today, the few remaining World War II aircraft still flying almost all use descendants of Caldwell's designs. The B-17 Texas Raiders, the B-29 Fifi, the countless P-51 Mustangs, P-47 Thunderbolts, and F-4U Corsairs at air shows worldwide. Listen carefully when they start up. That distinctive sound of the engine settling into steady RPM, that's Caldwell's constant speed governor at work, automatically adjusting blade pitch to maintain optimal performance. The crazy propeller design that made American fighters faster, higher climbing, and more combat effective wasn't crazy at all. It was brilliant engineering built on rigorous testing, deep understanding of aerodynamics, and unwavering commitment to solving problems the right way. Stand at the National Air and Space Museum in Washington, D.C. Look up at the aircraft suspended from the ceiling. The P-51 Mustang, the F-4U Corsair. Each one spins a propeller descended from Frank Caldwell's designs. Walk through the New England Air Museum in Windsor Locks, Connecticut. There sits an actual Hamilton Standard hydromatic propeller, the ASME mechanical engineering landmark. 4 aluminum blades scarred by decades of use, each blade capable of rotating independently through its full pitch range. It looks almost ordinary. Just a propeller, metal blades attached to a central hub. But understanding what those simple components represent, the physics, the hydraulics, the control systems, the decades of development, reveals the extraordinary nature of ordinary objects we take for granted. Modern propeller aircraft still use variants of Caldwell's design. The Lockheed C-130 Hercules military transport, 4 Hamilton Standard propellers, each automatically adjusting pitch thousands of times per flight. The Bombardier Q400 airliner, Dowdy propellers using descendants of the same hydraulic constant speed principles Caldwell pioneered. Even wind turbines generating electricity use variable pitch blade control. The same basic concept Caldwell developed for aircraft propellers. The numbers tell part of the story. Those 500,000 World War II propellers, the 15% efficiency improvement, the 600 feet per minute climb rate increase, the 100+ MPH speed improvements, the countless lives saved by feathering capabilities. But numbers can't capture the human dimension. Think about a B-17 crew limping home over the North Sea after a bombing raid on Germany. One engine destroyed by flak. The pilot hits the feather button. The propeller streamlines. The aircraft continues flying. 10 men get home. 10 families don't receive telegrams. Think about the P-47 pilot climbing to intercept German fighters. His paddle blade propeller efficiently converts 2,000 horsepower into upward momentum. He reaches combat altitude before the enemy closes. He survives the war. He comes home, raises children, lives a full life. Because an engineer in Connecticut obsessed over propeller blade geometry. Multiply those scenarios by thousands. Tens of thousands. That's Frank Caldwell's real legacy. Not patents or awards or plaques, lives. There's something profound about engineering done right. The best technical solutions become invisible. They just work. Pilots didn't think about their propellers constantly adjusting pitch. They just pushed the throttle forward, and the aircraft performed as expected. That seamless reliability? That's mastery. Caldwell never sought publicity. No grandstanding. No dramatic pronouncements. He just showed up every day for decades. Tested propellers, analyzed data, refined designs, solved problems. That quiet competence built the foundation of American air power. Today's aviation operates at a fundamentally different level than 1917 when Caldwell first walked onto McCook Field. Jets dominate. Satellites navigate. Computers fly aircraft. The technology is nearly unrecognizable, but the principles remain. Understand the problem completely. Test rigorously. Design for reliability. Make complex systems as simple as possible. Improve continuously. Those principles are timeless. So the next time you see a vintage warbird at an air show, listen to the sound of that engine and propeller. That steady, powerful drone of an R-2800 or a Merlin spinning a constant speed propeller. That's history you're hearing. That's Frank Caldwell's legacy, still echoing through the sky. One engineer's crazy idea turning at 1,500 revolutions per minute, pulling us forward into the future. Still flying, still working, still brilliant.